So given that we have carefully looked at the EM algorithm front and center, right. So we have looked at the description of the EM algorithm, we have looked at the correctness of the EM algorithm, and we have also looked at the background concepts required to understand a mixture model, right. So which the EM algorithm is helping us to learn the parameters of, right. Let us now actually apply this EM algorithm to solve different biological tasks or analyze different types of biological data. We will start with a simple application, okay, and again in each of these applications we will first introduce the mixture model and then we will show them how to do these three tasks, right. So this generative modeling task, this inference task, and this parameter learning task, the final task being the important task that EM algorithm is interested in solving, right. So the EM algorithm helps us to solve. So let us look at it in terms of a toy or warm up application first before going into other bioinformatics applications. And this warm up applications is a mixture model of two coins. It is also called as a Bernoulli mixture, okay. So it is a Bernoulli mixture model of two coins, okay. So what is the setup here? The setup is that you have two different coins, each coin has a different probability of coming up heads, okay. So the parameter really is that you have a coin A and a coin B, and we can also call it as a coin 1 or a coin 2. These are just other names, another name for A and B, right. And so you have these two coins, each one of them has a different probability of coming up heads, okay. So the coin A has a theta A probability of coming up heads and coin B has a theta B probability of coming up heads, okay. Maybe A coin is most likely going to give you heads, maybe theta A is 80%, okay, and then theta B may be it's half heads and tails, so theta B may be 50%, okay. So this is the probability of coming up heads in a particular toss of the coin, okay. And sometimes we will also refer to this as theta 1 and theta 2, because the coin A we are giving it an alias of 1 and coin B is given an alias of 2, okay. So we want to now figure out this theta 1 and theta 2, okay, given some data that we have observed from flipping these two coins, okay. And how are these coins flipped? It's a somewhat kind of a different setup. So you just have multiple sets of flips and each flip you have 10 tosses per set, okay. So you have 5 sets here that are being shown, okay, and then each of the set you can choose with half probability whether to choose a coin A or a coin B, okay. So this one, your pi 1 in your mixture model is half and your pi 2 is also half, okay. So pi 1 equal to pi 2 equal to half, okay. So you choose randomly, uniformly at random between the two coins, okay, and when you start one set, okay, this is set 1 and this is set 2 and so on till set 5, okay. So you do multiple sets of coin flips, coin tosses, and in each set you do some number of tosses, okay. So m tosses per set, okay, m tosses per set, here m is 10, okay. So you first go ahead, so the generative model view is that you first choose uniformly at random between these two coins, okay. So that is with probability 1 over half, 1 over half, okay. So equal likelihood to choose either coin A or coin B for every set, okay. Once you have that, then coin A has a certain probability theta f of coming up heads, maybe this is let us say 80%, and then maybe this is 50%, okay, and coin B may have a 50% of coming up heads and 50% of coming up tails, okay, and then coin A may be 80% of coming up heads, okay, that is given by theta A, okay. So now so this is your pi 1 and this is your pi 2, okay. Now you do whatever coin you have chosen, right. So now you do 10 tosses of the chosen coin. If it is coin A, you do 10 tosses of coin A, one of the two coins, and coin B you do 10 tosses of coin B, okay. And that is what is shown here. So initially people have chosen coin B here, and then you see that you have mostly some set of heads and tails, and then there is 5 heads and 5 tails, so it's more or less equal. Then in the set 2 you chose this path, right. You have uniformly at random choose one of the coins, you ended up choosing coin A, right. And so in set 2 you have chosen coin A, and then you can see that it is mostly heads, right. So 9 heads and 1 tails, and that is from coin A in the set 2, right. The first set was coin B, Again set 3 it's mostly heads again, but 8 heads and 2 tails. Set 4 you went along this route, right. So, pi 2 equal to half, that choice is being randomly chosen, and so then you have again a similar number of heads and tails, 4 heads and 6 tails, right. And then finally set 5 you choose A, and then you have a lots of heads, you have 7 heads and 3 tails. Okay. So, this is how your mixture is being generated. You can see here that for each of these sets, right. So, you will have a z variable. So, this will be z1 and z1 will be coin B, right, and then z2 will be coin A, z3 will be coin A, z4 will be coin B, and z5 will be coin A, right. And then if you call coin A as 1 and coin B as 2, then z1 is going to be 2, z2 is going to be 1, z3 is going to be 1, z4 is going to be 2, and z5 is going to be 1. Okay, I hope that is clear. Okay, and so you have this z which tells you which coin we have used. Used to flip 10 tosses, right, and then you have your x, which could be the number of heads in your set of coin tosses. Okay, so number of heads. This is also known as the sufficient statistics. This is all the statistics that you need. You don't really need the order in which the heads and tails are coming up in these 10 tosses. You can just summarize it into the number of heads and number of tails, right, and that is what we really need to do certain downstream analysis or probability calculation. So, these are called sufficient statistics. These are sufficient to do our downstream analysis. Okay. So, these are the so x could be the number of heads, right, and if you know that m is 10, right. So, m is the total number of tosses. So, m equal to 10 tosses, then your number of heads is going to be x, then m minus x is going to be the number of tails, right. Okay, so, this is shown for a single data point z and x, but you can also make it very explicit by saying that zn is for set n, nth set, what coin is being used, right. So, zn equal to 1 means coin A was used, zn equal to 2 means coin B was used. Okay, and then given that, then xn could be the number of heads in that set n, right. And so, if you take an example z4 here, right, is 2, which means coin B was used, and then when you use coin B, then you look at xn, which is the number of heads that are observed, and in this particular case xn will be 4. Okay, 4 heads were observed, right, and then m minus xn is going to be the number of tails. M is 10, so 10 minus 4 is 6, so that 6 is going to be the number of tails that are observed. Okay. So, that is how you can look at this model, and then you can put a box around it to say that this is just replicated for all n from 1 to capital N. Okay. In this particular case, the capital N is 5. Okay. There are 5 sets that are being used. Okay. And so, this is how you generate the data, right, and then when you generate the data, you know both Zn and Xn, right, and then later on you can choose to throw away and ignore Zn, okay, because the actual data that comes in, you only know Zn, and then you don't know, you only know Xn and you don't know Zn. Okay, that is the latent or hidden variables. Okay. I hope the model is clear now in this term of mixture model of two coins, right. And how would you do inference with the model, right? So, we have seen the generative modeling view of this mixture model. How will you do inference with this model? When the inference with this model, like I said, we do not know what coin generated it, right? So, these colors and other things are not there, and then even what coin generated it is not there, right? And you only know this table that is shown here, right, and then you do not know whether coin A or coin B has generated it. You just know that in the set 1 x1 is 5, right. So, x1 is 5, x1 is the number of heads observed in set 1, right, x2 is the number of heads that is observed in set 2, x3 is the number of heads that is observed in set 3, and so on, right. All you know is this, right, the number of heads observed. So, 5, 9, 8, 4 and 7. Okay, you do not know which coin was used to generate that set of heads, and m is the total number of tosses. So, if you just subtract m minus xn, you will get the number of tails. Okay. Now, the standard inference questions are, you need to calculate what is the likelihood of a particular data point being generated, what is the probability of xn given that there are some values theta. What is your theta here? Theta is going to be pi 1 and pi 2 for choosing between the two coins, right, and then you have theta 1 for the coin A and turning up heads, and theta 2 for the coin B turning up heads. Okay, and we are going to assume that both coins are going to be a priori used equally likely. So, these both we are going to assume it is known and fixed at half. So, really your theta is only going to be the probability of the first coin coming up heads and the probability of the second coin B coming up heads. Okay. So, this is theta 1 comma theta 2, right, and so this is going to be, because I do not know which coin was generating it, right. So, then I have to just say that this is the half probability that coin A generated it, and then there are xn heads, then that is theta 1 raised to the xn, and then there are m minus xn tails, right. So, that is going to be 1 minus theta 1, right, m minus xn, plus there is a half probability that coin B would have generated it, and that has theta 2 probability of coming up heads, and there are x of n heads, and then 1 minus theta 2 m minus xn for the tails, right. And you can simply write it down as sum over Zn, right. Zn goes from 1 to 2 for the 2 coins, half probability for the coin to be selected, and then you have this theta Zn probability, right, for generating each of your xn heads, and then 1 minus theta Zn for all the tails m minus xn, right. So, this is your marginal probability, right, and then if you have this term is the term 1 and this term is the term 2, right. If you want to know what is the responsibility vector Rk of n, right. So, this is defined as this probability that z is k, right, given you have x equal to xn and then your current set of parameters theta, right. So, this is your responsibility vector or the posterior probability, right, for every set, right. So, for this set what is the coin that would have generated this particular data, right, what is the probability that coin A would have generated 5 heads, and then for x2, right, what is the probability that coin A would have generated 9 heads, and so on, right. So, that you can ask for any value. So, if k equal to 1, that is probability that coin A generated this particular set of heads, right. If k equal to 2, then it is a probability that coin B have generated this set of heads, right. So, how will you do this? So, this is this essentially this 1 over 1 plus 2 or 2 over 1 plus 2, right, whatever the k is, then that is how it is done, right. So, probability of z equal to 1 given x equal to xn comma theta is going to be 1 over 1 plus 2, these two terms, right. Probability of z equal to 2 given x equal to xn and this theta is going to be 2 over 1 plus 2. Right. This is just simply normalizing 1 and 2 and then converting them into probabilities, and this is what Bayes theorem will also do, and this is what we have seen also in our earlier task when we were reviewing these two probabilities, right. Okay, so let us look at a responsibility vector of this particular data point x1 of x1 equal to 5, right. So, what is the probability that coin A generated this set of 5 heads, right. So, then that probability is given here. So, this is the probability that z equal to 1 given your x equal to 5 x1, okay, and given all of your theta 1 and theta 2, okay, and this theta 1 and theta 2 is going to be 0.7 comma 0.5, right. If you have this, then this will be your responsibility vector, right. So, the probability that coin A would have resulted in 5 heads. Here it looks like coin B is 50% probability of coming up heads and 50% probability of coming up tails. So, this term will be larger, and because of that this whole thing will be some value that is less than 0.5. Okay. So, the first set x1 equal to 5 is more likely to be generated by coin B rather than coin A, okay, because coin B is equally likely to come up heads and tails, but coin A is 0.7 probability. It is a very high probability of coming up heads, and then but in actuality we see equal number of heads and tails 5 and 5 in this particular set 1. Okay. So, that completes our understanding of the inference calculation using this model. Now, let us go to the actual meat of the thing, which is parameter learning, right. How do you do parameter learning in this setup? In order to do that, we will do it in 2 steps. We will just do parameter learning using the complete data as a warm up, where you are observing both the x and the z. So, you are kind of put back the coin labels and you have put back all the colors, and you know which coin was used in each of these sets, right. and then it's an easy problem to do maximum likelihood estimation. Then we will look into the observed data where only the x's are observed, these numbers are observed, but you do not know the coin labels. Okay. When you have a complete data, then the likelihood is simply this probability of observing the set of data points, right. So, you have all the data points n equal to 1 to n, and then you have theta zn to the xn and 1 minus theta zn to the m minus xn for the heads and the tails, right. And this 1/2 probability is for choosing that particular coin, either coin A or coin B. We just assume pi 1 equal to pi 2 equal to half, right. Now, if you have this, right, and then you are looking for the theta 1 and theta 2 that maximizes this likelihood, right. If you use standard calculus and then look at what will be the theta 1 and theta 2 that is the maximizer of this likelihood given a set of data points x and z, the complete data, right, both the observed data and the label z are both revealed to us, right. So, then it will turn out that it is this intuitive formula where you just look at all the sets where coin A was used, right. These are these 3 sets where coin A was used, right, and then you just add up all the heads there, which is 9 plus 8 plus 7, that is 24, right, and then 1 plus 2 plus 3, that is 6, right, and then use this two numbers 24 and 6, there are totally 30 coin tosses here. So, then this is the maximum likelihood estimate for the probability of heads for coin A, theta 1 is going to be 24 divided by 24 plus 6, right, 24 divided by 30, and that is roughly 0.80. Okay. Similarly, for coin B, right, you know that the first set and the fourth set were generated by coin B. So, that label, using the label Z, we know that. Then you are looking for the maximum likelihood estimate for theta 2, right, what is the probability that coin B will turn up to be heads. Then all you have to do, look at all the tosses of coin B and how often heads came up. So, you have 5 plus 4 9 that heads came up in out of 20 different tosses. Okay. So, 9 divided by 20 will be your answer, and that is going to be roughly 0.45. Okay. So, that is really the maximum likelihood estimate if you knew the complete data. Okay. So, there is a nice closed form solution, and you can write it also in this way, right. Let us say that we define this term Rk of n to be the following. So, Rk of n is like a one hot encoding vector of z of n, right. So, Rk of n is going to be 1 if zn equal to k and 0 otherwise, right. So, if coin A was used, then this Rk of n vector across this k equal to 1 and k equal to 2, right. If coin A was used, it is going to be 1 comma 0, and then Rk of n, if coin B was used, is going to be 0 comma 1. Okay. So, if coin A was used, then you know that Zn equal to 1. If coin B was used, you know that Zn equal to 2, right. So, this 1 and 2 is just converted into this one hot encoding vector 1 0 and 0 1, and so that is how you define this responsibility vector Rk of n in this hard fashion. Okay. It is 1 if Zn equal to k and then 0 otherwise. Okay. If you have that, then if you look at this, right, it is essentially doing whatever calculations we are doing here, right. So, here we are saying that I want to collect only the heads where coin A was used, right, and that is what will happen. So, if theta k equal to 1, then Rk of n will only be 1 for those sets where coin A was used. Okay. So, then you just multiply that with the number of heads xn, right. So, xn is 9 here, xn is 8 here, xn is 7 here, right. So, then all of those 3 numbers will be added up, and that will give you the total number of heads, that is 24 here, right, and then divided by Rk is going to be the total responsibility. Okay. So, Rk is going to be sum over all the data points Rk of n. Okay. This is how we will define the total responsibility for component k. Okay. So, total responsibility of component k. Okay. And this is the responsibility of component k for data point n, right, xn, right, and here we are just summing up over all the data points, right. So, in this particular case, the 3 sets where coin A is used. So, R1 is going to be 3, right. So, R1 is going to be 3, and then R2 is going to be 2 sets where coin B is used. So, R2 is going to be 2. Okay. So, then that will give you this m is going to be 10, right. So, the 10 tosses that are being used. So, you will just see here that in the denominator here there is 30, right. So, the numerator, this whole sum will give you 24, and then the denominator will be 30, right? And then similarly, if you change theta k from 1 to 2, right, the numerator will be this 5 plus 4, that will give you the sum over n rk of n xn, and then the denominator will be 20 times 10 plus 10, right, 10 times 2, that is this rk times m is 10 and rk is going to be 2. Okay. So, then you will get this 9 over 20. Okay. So, I hope this formula is clear, because we will use this formula again and again later, even when rk of n is not 1 and 0, but they are fractional. Okay. But in reality, we only observe x and we do not know z is hidden, and this calls for the EM algorithm, right. And in the EM algorithm, you are not maximizing this particular likelihood that is shown here when you have the complete data, but you are actually maximizing this marginal likelihood where you do not know the label z, right. So, that z is taken away, and then because of that you have to sum over the uncertainty of the label, right. So, which of the coins was used to generate that particular set of heads and tails, right. So, that sum over Zn goes from 1 to 2, right, and then you have the rest of the terms in the equation remain the same. Okay. But because the sum is introduced, it is a more complicated function to optimize, and then that means that we have to do this E step and M step. So, if you want to apply this EM algorithm to our Bernoulli mixture of two coins, right. So, these first two steps are simple, right. You just start at some initial parameter value theta naught. So, that we can do, we can just start with 50% of probability for the first coin coming up heads, and the second coin also you can start with 50%, right. So, theta naught can be 50 comma 50, right. So, the values for the heads for the two coins. E step is also easy, we have already seen it in inference. For each data point in your total set of data points D or D capital N, right, if there are capital N data points, then you can compute the posterior, right, you can compute the posterior, which is you can compute the posterior, which is this P of z given x using the current set of parameters theta t, right, the iteration is given by theta t, right. And so, this is also, we have said that this is also can be represented using this responsibility vector rk of n, right. So, which is this probability that z equal to k given x equal to xn using the current set of parameters theta t, but I am going to just call it theta t to avoid confusion with the theta 1 and theta 2 used for coin A and coin B. Okay. So, this is also, so this is done, this is also done. So, all we have to do is only look at this M step, how do you maximize this complicated looking function, and we have already said that even though it looks complicated, this is more like a complete data log likelihood. So, complete data log likelihood, because you can see that there is x and z both are being observed, and so you have p of x comma z given theta as a function of theta is going to be the likelihood, and so you have a log likelihood of the complete data. But of course, you only know x, we do not know what z is, and that is going to be imagined or filled up, right, or hallucinated, they also use the word hallucinated, that is going to be drawn or hallucinated from this posterior distribution P of z given x using the current set of parameters theta t. Okay. So, the z is going to be drawn from that, right. So, this is also called as hallucinated or expected, because this expectation is taken over all such z, right, that is drawn from this posterior distribution. So, this is the hallucinated or expected complete data log likelihood, and that I want to maximize, right. So, how can I think about it? How can I get the theta t plus 1 given theta t? Okay. And that is what is shown in this slide. So, how do you do this M step optimization? And you can do the M step optimization by thinking about it also as another MLE problem that is similar to the complete data log likelihood. So, you are using the same formula from before. This is the formula that we have used in the complete data log likelihood, right. But there this rk of n was either 0 or 1, it was in one hot encoding of the known label of each set, right. But here I do not have a 1 0 label, I do not have a hard labeling of each set of coin tosses that are shown here, but I have a probability, a fractional responsibility, right. I do not have a 0 1 responsibility. Your rk of n is your fractional responsibility for probability that z equal to k given x equal to xn using your current set of parameters, right. So, your current set of parameters in iteration t, right, And so using your current set of parameters, you calculate this responsibility vector, which is now like this fractional vector. Like I said, it's no longer a 0 1, but otherwise your Rk is also going to be sum over n your responsibility of component k across all of your data points. All of those are defined the same. This is defined exactly the same as before. This is we know how to calculate it using our inference, and this formula is also the same, right. So, instead of having Rk of n being 0 and 1, so the main change here is that you allow fractional responsibilities, right. And then this theta k hat is now going to be the optima or the maximizer of whatever complicated function that we looked at in our m step. Okay. So, this m step optimization can be done using this simple formula plus given here, right, where you start out with theta t and then you get this theta k hat at iteration t plus 1. So, this is iteration t plus 1, okay. And then on the right hand side of the equation, your Rk of n and Rk are all calculated using your iteration t, okay. So, this is how you go from theta at iteration t to theta t plus 1 at iteration t plus 1, okay. So, this is a intuitive looking formula, which is essentially saying that you compute some kind of weighted average of the number of heads you have observed across all of them, across 5, 9, 8, 4 and 7, right, but then weighing them with the fractional responsibilities Rk of n and then doing some normalization, which is this Rk of n times m, where m is the total number of coin tosses, okay. Now, this is the full EM algorithm now that is shown here. If you know the labels, then this is your best estimate 80 and 45, right, but if you do not know the labels, then this panel is shown here on the right hand side. So, on the left hand side is maximum likelihood from complete data, on the right hand side is EM algorithm on the observed data. In the observed data, you do not know the colors, you do not know the coins that has generated them. So, you just have these gray colors for the series of heads and tails, right. In your E step, you calculate your Rk of n, your responsibility vectors. Then you figure out, let us say that this Rk of n for k equal to 1 is shown here and k equal to 2 is shown here, right. So, you have 0.45 comma 0.55 for set 1. So, both of those numbers are probabilities that add up to 1. That says that the set 1 is generated with 0.45 probability by coin A and 0.55 probability by coin B, right. And all of these Rk of n are calculated using your theta t, your current set of parameters, right, and theta 0 was chosen to be 0.6 and 0.5, okay. So, A has slightly higher probability of coming up heads, B has an equal probability of heads and tails, okay. So, all of these are calculated. Now, here is where this interesting thing comes up, this fractional responsibilities comes up, right. So, you have 5 heads and 5 tails here, right. You just multiply it with this 0.45 responsibility. You do not assign it either to A or B completely. You do not have your Rk of n be 0 or 1, that only one of these rows, right. So, one in this first row, only one of them have all 5 heads and 5 tails, right. You are just splitting it in this fractional way. So, in 45 to 55 ratio, you are splitting the 5 heads and 5 tails, right. So, which means that 2.2 heads comes to A and 2.8 comes to B, and the total of them is 5 heads, right. So, which is the 5 heads over here, and the 5 tails also split in 2.2 to 2.8 fraction, right. And similarly, the second one you have an 80-20%, right. So, you are now going to have the A coin is mostly responsible for the second row. So, you have 9 heads and 1 tail, right. So, 9 heads times 0.80 will be 7.2 heads, right, and then only 1.8 heads are assigned to B fractionally, right, and the one tail is also split in that way 80-20, right. So, you have 80% of that single tail is assigned to coin A and 20% is assigned to coin B, okay. So, the heads and tails are also split fractionally according to these responsibility vectors calculated in the E step, okay. Once you have all of these things, then you have this kind of hallucinated or expected complete data, right. So, you know all for coin A how many tosses were done, fractional tosses were done, and how many of them are heads, right. Similarly, for coin B you can add it all up, right. So, you have 11.7 heads and 8.4 tails and 21.3 heads and 8.6 tails, right, and then the total number of tosses done is 21.3 plus 8.6, right. So, out of all those 21.3 comes up to be heads, right. So, this equation here, which adds up all of this to get 21.3 and adds up all these fractional numbers to get 8.6, and this 21.3 divided by 21.3 plus 8.6, this normalized value, which turns out to be 0.71, is exactly the formula that we showed here, right, this sum over n rk of n x n divided by rk into m, right. So, that is exactly shown here, and then the same formula where k is 2, the theta hat of b, right, b is coin b is z equal to 2, right, and so that turns out to be 11.7 divided by 11.7 plus 8.4, that is the total number of tosses, and so your initial estimate of 0.6 and 0.5 is now being updated to 0.71 and 0.58, okay. So, that is this update theta k hat step using this formula that is shown here, okay. And then you repeat this step using this 0.71 and 0.58, you recalculate your rk of n, you re-update your theta hat of k, and then you keep on doing it at some point, and so that is this m step, right, but at some point you are going to stop and then say that I have converged, and then you converge to a value that is 0.80 and 0.52, okay. So, that is the maximum likelihood estimate of the probability of coin 1 or A coming up to be heads, that is 0.80, and then the probability of B coming up to be heads is 0.52, okay. So, that completes our application of EM algorithm to the Bernoulli mixture of two coins, okay. And it sets the stage for some more interesting kind of real world biological data applications, right, and then this is where the EM algorithm meets motif finding in DNA sequences, okay. We have looked at different algorithms for motif finding, mainly this randomized motif search algorithm and a Gibbs sampling based algorithm, but we can also look at motif finding from the lens of EM algorithm, and EM algorithm can also be used to solve motif finding with certain advantages, okay. That is what we will look at next.